Alright, let's count some stuff. This video is all about permutations, or the number of ways or arrangements that an object can happen. Again, we talk a lot about counting when we talk about probabilities. So let's see how permutations might help us out when it comes to some probabilities. We've got a scenario here. We've got 3 different desks, and we've got 3 different ladies, Libby, Janie, and Maddie. So how many ways can Libby, Janie, and Maddie be placed in those 3 desks? Or how many ways can we make a seating chart, essentially? Well, obviously, we can sit Libby in the first desk, Janie in the second, and Maddie in the third. But what if we kept Libby in the first desk, but put Maddie in the second desk, and Janie in the third? Or even better, what if we put Maddie first? Well, what are all the ways that that can happen? Well, there we go. We've got all the different seating charts here. Again, Libby in the first desk with either Janie or Maddie in the second and the other one in the third. What if we put Maddie first? Again, we could flip-flop Libby and Janie. Or if we put Janie first, again, we've got Libby and Maddie switching places. So again, how many ways can this happen? Well, it looks like we've got 6 total possible seating charts that can happen. If we only let one of them sit, if there were only one desk, how many ways could that be selected? Well, basically it's only one desk, which means in that one desk we've got 3 options. I would say there are 3 ways in which that one can happen. And if one desk was broken, how many different ways could 2 people still sit? Well, the trick there is, well, there could be 3 people who sit in desk 1. There could be 2 people who sit in desk 2, but since there isn't a final desk, there are 6 total ways still that they could be seated there. The third person just ends up standing. And if we really think about it, that initial number, there were 3 people to pick from, then there were 2 for the second desk, and the last person got the last desk. So we're sort of counting our way down those numbers. Now, those ones were easy enough to count on their own, but what about the scenario at the bottom? What if Maria wants a new phone number, but really doesn't want it to have any repeating digits? No numbers allowed to be used more than once. So the numbers 0 through 9, again, 10-digit phone number using 10 different numbers. How many different ways could that happen? Well, if we really think about it, there are 10 numbers to choose from, right? 0 through 9 for the first number. Then there are 9 numbers to choose from for the next one, and so forth and so on. And by so forth and so on, I mean counting our way all the way down to that last digit. So we've got 10 digits, 9 digits, 8 digits, again, 8 numbers to pick from for the third possible digit, but then there's only 7 to pick from for the next one, and so forth and so on. Again, if we multiply all those together, 10 possible digits, and 9 to pick from, and 8 to pick from, usually when we say that word and, right, there were 3 people to choose from for desk 1, and 2 people for desk 2, and 1 for desk 3. We usually multiply, and usually means multiply. So multiplying the digits from 10 to 1, we end up with 3,628,800 different possible phone numbers. Now, that idea of counting down from a high number down to a low is what's called factorial. 4 factorial, or 4 exclamation point, right, the product of integers from 1 up to n, or what I often think of as n down to 1, is called n factorial, n exclamation point. So 4 factorial is 4 times 3 times 2 times 1, which would come out to 24. So if we're looking at the 3 on the left here, we've got 2 factorial, which would be 2 times 1, obviously coming out to a 2. 8 factorial, which is going to be a little bigger, and 15 factorial. So again, counting those numbers from 15 down to 1, but multiplying all their digits. Feel free on your calculator to type in those numbers. Now, if I was doing 15 factorial, though, I don't really want to type all that out. So one thing that I might do is use the factorial key on my calculator. And on your calculator, one way to do that, if you have a graphing calculator, is go to your math button. Again, it's 2 buttons below second there, just in the upper left. If we press math, it's going to take you to a screen that looks much like the one on the right here. And all I want to do is arrow either 3 to the right or 1 to the left. Go to this PRB menu. That's the probability menu. It's got a lot of options for ways to count and or do probabilities. And you'll notice the 4th option down is factorial. So what we'll do is just press number 4. Now realize again, we wanted to do 15 factorial or 8 factorial. So let's do the 8 here. So I'm going to type in, instead of answer there, I'm going to put 8. I want to put that in front of my factorial. And then when I press enter, I won't have to actually type out 8 times 7 times 6. All I have to do is just write down my number. So 40,320. So again, oftentimes you might be able to just do these by hand. Obviously 2 times 1 is 2. But again, for 8 factorial, that was 40,320 using our calculator. Now you can do that same thing on a TI-30 calculator. If you press the PRB button, you'll notice it's just kitty corner, just to the right and down from that second button. There's a PRB button, and it'll take you to a menu that says NPR, NCR, and you'll notice the third option over again is factorial. So make sure you type in your number again beforehand. Now I don't have an example of how to do that on there, but on your graphing calculator it works the same way. If I press 1, 5, I want to put my number in first. Again, go to Math menu, which again would have been that PRB button on the other calculator. So I got to go over to that menu, and again hit number 4. And it'll quickly figure out for me, well, that's a big one. Then notice that scientific notation number, e to the 12th, which is actually 10 to the 12th. So 1.308, if I round a little bit, 1.308 times 10 to the, I forgot my number, 12th here, 10 to the 12th power. And we know that's a very, very large number. And again, the only time we ever use x for multiplying, scientific notation, when those numbers either get really tiny, or in this case, for factorials, really big. Now, one side note about factorials is that we often find 1 factorial, which you can't really count your way down to 1 when you start at 1. So again, that's equal to 1. We also need a way, and we'll find out here in just a little while, to find 0 factorial. Now, obviously, that's counting your way up to 1. And if we were multiplying, well, multiplying by 0 would always be 0. So we just define it that way. 0 factorial is equal to 1. We need that to happen in order to help us with things called permutations. And we'll also need it when we get to combinations. We'll talk about those in the future. Permutations, though, are the number of ways to arrange. So like thinking about our people sitting in their chairs, the number of ways to arrange people in order, or arrange things in order. What if we weren't sitting all 7 people in all 7 chairs? What if we don't want 7 factorial? Right? Factorials work great when you're counting your way all the way to 1. But if we only have 3 chairs, we can only sit 3 people. But remember, there would be 7 people sitting in the first chair, or 7 possibilities of people to sit in chair 1, times 6 possible in chair 2, and 5 possible in chair 3. Well, we want a faster way to do that. So permutations, or you'll notice here 7p3, is sort of the number of ways to pick 3 people out of the 7, or 3 arrangements, 3 orders, right? If order matters, order still matters. Think about seating charts. It's different whether you get a desk, but it's also different whether or not you get the first desk or the last desk. The order matters. Well, the function just says, let's take that n, so we're going to say 7 factorial on top, divided by n minus r. So it would be 7 minus 3 factorial, notice the parentheses, so factorial on the outside, on the bottom, which basically comes out to 7 factorial over 4 factorial, which if we really think about it is 7 times 6 times 5 times 4, 3, 2, 1, over 4, 3, 2, 1, and we'll just cancel out those 4s and down, and we end up with what we expected, 7 times 6 times 5, or basically 210 different ways that can happen. On a small side note, if you are picking all of the numbers, npn or 7p7, think of it that way. Again, that's 7 factorial over 7 minus 7. That would be that 0 factorial. There's where I was saying 0 factorial is 1. So we'd be dividing by 1, and basically it really wouldn't matter. N factorial. How many ways can you seat 7 people in 7 chairs? Well, 7 times 6 times 5, all the way down to 1. Take a second, think about how we could use those ideas, factorial and permutation. Where would they apply for these two questions? All right, well, hopefully you got the same answers that I did. Again, if Nick's band's recording 12 songs and all 12 are going to make the CD, but note we want the arrangements. We care about the order in which that happens. Then we're going to just say 12 factorial. There are 12 songs that could go first. There are 11 songs then that could go second, and so forth and so on. So 12 factorial coming out to 479,001,600. If we're only choosing 8 of the 12 songs, well, again, that's a permutation. We only want a certain number of. So 12, pick 8 of them. 12 factorial over 12 minus 8, or 4 factorial. And again, if we work out the math, we've got our 1,995,8400, about 19 million, almost 20 million ways of making that happen. Now, you can also do permutations directly on the calculator. So you'll notice on the screen here, I've got 12 NPR8 typed in. I'm just going to retype again. I'm going to type that first number, N. Then again, go to my math menu, or on my TI-30 calculator, hit that PRB button. Again, I'm going to go to that PRB menu, and you'll notice NPR is one of your options. So I'm going to press number 2, and again, pick number 8. And there you go. So again, pretty quick and easy, taking advantage of our calculator to find these very large numbers. These are not the number of things we'd want to count out. A tree diagram would not go well when we're choosing 12 songs and trying to decide what can come next. Let's try one more idea and see how we can apply this to probability. Take a second, read through the problem on here, see if you can't answer questions A, B, and if you think you can do it, try part C. All right, well, hopefully you came up with what I did. Up here at the top, in how many ways can all the floats be ordered? Well, again, there were 12 floats to pick from, but no float can go first and second, or second and third. So again, 12 to pick from for slot 1, 11 to pick from on slot 2, and down and down and down until there's only one float to follow up at the very end, which means 12 factorial. On the second answer, though, or second question, they're saying, oh, wait a minute, though. What if, right, the soccer float gets to go first? Well, there's only one soccer float to pick from. Then there's only one choir float to pick from. So 1 times 1 at the very beginning. Soccer float and choir float. And they get followed up by all the other floats. So 10 factorial to finish. 10 times 9 times 8 times 7, all the other options of who could come next. Well, 10 factorial times 1 is really just 10 factorial. We've got our number here, 3,628,800. And finally, what's the probability that the soccer float's first and the choir float is second? Well, all the ways in which that can happen, divided by all the ways to organize 12 floats, comes out to 0.182. That's the probability of, again, soccer, then choir, then everybody else. I hope that helps you again with counting. Helps you a little bit with probability as well. Enjoy those factorials, work those permutations, and have a great day.